Hello everybody, my name is Jorge and I'm going to talk about the problem about using a square section. This is the problem right here. Now what can we get about this problem? First, definition parameters. The load, 5,000 kilonewtons. Soil layers. The first layer is the safety gravel on Hassan, and this is the data that we can get about all the problem. Layer 2 and 3 are clay of high plasticity. Both. So, what are the data we can get about this? First, the depth. Second, the undrained shear strain. The gamma of the soil saturated of each one. Next step. First, what do we need in order to make a pile? First, we need to calculate the shaft capacity. For layer 1, that is almost a sand. For this layer, we're going to use the formula that uses the factor K, which is the air pressure coefficient, and the friction between pile and soil. This one. And third, and effective vertical stress. This one here. Layer 2 and 3, since both are clays, the shaft capacity is more simple here. We only need the adhesion factor alpha, that for clay is 0.9, and the undrained shear strain, this one. This is going to give the shaft capacity per unit length. Step 2. Tip capacity. Tip is going to be in the third layer, we already know that. And we know that that layer is a clay, so we're going to use this formula right here, where the factors NQ and NC, when the angle is 0, both are 1 and 9. Step 3. Pile dimensions. What do we know about our pile? It's a square. What do we know about squares? We know how to calculate the area and the perimeter, and both are needed for the load of the shaft and the load of the tip. So, we have the data, we have the formula. Step by step, the process that we are going to use. Step 1. Effective vertical stress plus shaft capacity. For layer 1, we have the data. Vertical stress is the gamma of the soil multiplied by the depth divided by 2. Why divided by 2? Because it's a sand. So in all the sands, the effective vertical stress only applies in the middle of the layer. So that's why. This data, and finally the shaft capacity per unit of length for layer 1. Layer 2 and 3, same formula. Alpha is equal to 0.9. Shaft capacity per unit length is equal to that same factor plus SU1 and SU2. That's the only thing that changes for these two layers. Now, step 2, tip capacity. Layer 3 has all the job here. What are we going to use for the tip capacity per unit length? Per unit area, it will be 9, this factor, because we already talked about the factors, plus C, and this is the result. Now, pile dimensions. We're going to start with a simple dimension, 1 meter, and it's a square section. So, for all the load of the shaft 1, 2, and 3 by the layers, it's going to be QS1 multiplied by the perimeter cross the depth. Layer 1, 5 meters. Layer 2, 3 meters. Layer 3, we're going to assume that's going to reach the end, so 25 meters. This is the total load of the shaft altogether. Now, the capacity, QB multiplied by the area. The area of a square, we all know it. So, final step, we gotta add all the load of the tip, the load of the shaft, and now we're gonna divide all that for a factor of safety, which is 3. We choose that. Now, we can see here that the result is 6,000 kilonewton. It works. Yes, it's going to do the job, but that's how to say it, oversized by one whole kilonewton. So let's reduce the height in layer 3. You can also reduce the dimension. That's another way you can do it. But for this example, let's go with the height. If you reduce the height in layer 3, what's going to change? Shaft 1, the same. Shaft 2, the same. Shaft 3, okay, we're not going to play with 19 meters. Shaft 3, we're going to change. So, this result different. Tip capacity, you haven't changed nothing else, so the same. Final step, different result. Same factor, but now our whole load divided by the factor 5.2 kilonewton per thousand. So it works and it's not oversized, so it's a good solution. Thank you for watching.
Okay, hello everybody. My name is CEDEñO. I'm working with my partner Lee Tovar, Jorge Lee Tovar. Well, we're gonna talking about a little exposition about this homework. Is a little structure of three layers. Well, the topic is the critical consultation in Guayaquil has a mandate project which is constructor of five-story buildings. According to the structural engineer, the highest recorded load of the land columns in 5,000 kilonewtons. It requests to design a pile that can support in load those both shaft and type and tip capacity. Both of the length and across and the cross-sectional dimensions should be defined by you. Design circle and square sections. Note, which is very important, you may apply any methods discussed in class for the guide text. Okay, well, in my exposition, we're gonna talk about the circular section. So in total, we have three layers of 5 meters, 3 meters, and 25 meters. We have these three type of layers, and this is the phreatic level. Okay, for this part, sorry. First of all, we're gonna define the parameters. This is the process of the circle section. Okay, well, first of all, we're gonna define the parameters, the load that the problem says that is 5,000 kilonewtons. First of all, the soil layer for number one, have a depth of 5 meters, angle of 40 degrees. The section, the C, this part, this part, the C, we're gonna talk about next in the next paper is 100 kilopascal. We have a structure of 19.4 kilonewtons meter cubic, and we have a heat that for the layer we have that it needs 15 hits per meter. The second layer have 3 meters of depth, 98 kilopascal, 17.2 kilonewtons cubic, and we have an angle of 0 degrees. For the third layer, for this part, we have the layer have a depth of 25 meters, 180 kilopascal, have a saturator that have 80.3 kilonewtons for cubic and have a zero degrees angle. Okay, first of all, we consider the calculating shaft capacity, granular soil for the layer number one. For the granular soil, the shaft capacity is given by is equal to K, the angle to tan tangent of tangent the angle. When the K is the air pressure coefficient, when we can assume that K is similar to 1 for simplicity. We have this is the efficient vertical stress, and the other the other topic is the bisolid friction applied can be as can well we're gonna assume that for this topic is 0.7 plus, sorry, not plus, for the angle. Okay, well, we're gonna calculate this parameter that we don't know. So gentry Q is for this layer. The coefficient soil layer for layer two, we have the same formula that we have Q is equal to alpha SU, where the alpha is adhesion frac adhesion fact ad, adhesion factor often takes 0.9 for the clay because these ladders means that have a clay hard or hard clay. Yeah. For SU, that is the problem, say to us, is 98. This is the on the river shear stress for soil. We calculate is QS, sorry, we'll calculate QS for each cohesive layers. And for the calculate the tip capacity QB is gonna say the NQ, this topic, plus NC plus C, where NQ and NC are varying capacity factor than dip on the angle. For the angle is equal to 0, NQ is 1, and NC is similar to 9. Sorry. Well, next we'll terminate the pin length and the dimensions using the total capacity shafts plus type, plus tip type. The pile and the cross-section dimensions are calculated for ensure the total capacity meets or exceeds, not exceeds, exceeds 5,000 kilonewtons. For the circle section, we're gonna have for the Q shaft, it's a summatory of QS, the the variability P, the D, the diameter, LT, the large of the pile, and the Q trip, the Q tip trip. Yeah. For this is the QB point P diameter cubic, no, quadra, diameter, elevate, and all two. The in the divide for four. Yeah. The next part is iterative design. Well, do you have the selection initial dimensions? We have the diameter. We're gonna consider 1 meter for the diameter. Sorry, for calculate for and calculate the capacity. Well, for the calculation for detail for the fifth layer, we have the details. First, the first calculation is effective vertical of all the middle of the layer. We have this formula, and we're gonna do we wanna replace the for the real numbers. That is the 19.5 multiplied by 5/4. We're gonna have 48.5 kilopascal. The friction angle for pile soil interface is the formula that we talk about in the other paper. We're gonna replace the real numbers and we're gonna have 0.7 for 14, and we're gonna have the angle is 28 degrees. For the shaft capacity per unit length, we assume the K is equal to 1. QS is equal to the formula that we talked about, we got talked before. QS is equal to 48.5 times of 28 degrees. That this is equal to 25.779 kilopascal. Okay, for the next layer, we're gonna use these details using the angle is 0.9. The shaft capacity per unit length is equal, the Q is equal to alpha point SU is equal to SU. While we're gonna replace the real data, the QS is 0.9 multiplied by 98, we is gonna have equal to 88.2 kilopascal. For the layer 3, we'll have the details using alpha is equal to 0.9, the shaft capacity per unit length. We have the Q is the alpha plus ECU. Now we're gonna have the real details is 0.9 multiplied by 180, 118, 18. This is equal to 162 kilopascal. And next we have the capacity calculations for a circular type, a circular peel type. C is for the layer number 3, that is 180 kilopascal, and angle is 0. The S0 NQ is equal to 1, and the NC is similar to 9. The tip capacity calculation, we have the tip capacity per unit RQB is equal to NQ for the angle, vertical, plus NC for C. Given that layers is cohesive, the angle is 0, the QB is equal to 9 for 180, and this is gonna be equal to 1,620 kilopascal. For the calculate the repeated pile, the pile dimensions, assume the material diameter is gonna be 1.2 meter for a circular pipe. The shaft capacity the Helio's capacity, we're gonna calculate the Q shaft is equal to the summatories of this formula. Um, but the final calculation we know that we have these three layers. So we're gonna calculate Q shaft for every of the three layers. For the QC, we're gonna have the Q shaft number one is 48, 48, no, 4,086.333, sorry, 32 kilonewtons. For the layer 3, the QS is equal, we're going to apply the real data. The QS number 2 for the layer 2 is 96.54 kilonewtons. For the layer 3, Q shaft 3 is 15, no, sorry, is 15,278.4 kilonewtons. We're gonna do a summatory of these three Qs and have Q shaft total. Yeah, we're gonna have this answer. And well, for the tip capacity, we're gonna have the Q tip is equal to QB, and the well, it's a circular section, so we're gonna use this area. Okay, for the Q total, for the Q tip capacity is this answer, 8031.15 kilonewtons. And for the capacity, for the total capacity, we're gonna do a summatory of the total of Q shaft and the Q tip. We have the Q shaft for plus Q tip is gonna be this answer of here in kilonewtons. Well, for the factor safety, we're gonna use a factor safety of 3. So we're gonna do a division of the Q total for the for the safety factor, for the factor safety. That is this answer. So in conclusion, we have the circular pipe with a diameter of 1.2 meters and a length of 33 meters. Total of the all layers, that is the total. We're gonna assume 5 plus 3 plus 50, 25 meters is the total of the three layers. We will safety support the load of 5,000 kilonewtons with factor of safety of 3. Thank you.